Today, we're going to be talking about how I stumbled onto AST quite on accident, how AST plays a vital role in the Kotlin compiler, and more namely, what 47 degrees is doing to grab onto the power of AST and enhance the power of the Kotlin compiler. All right, so shameless plug. I actually have a talk at the end of the day. Sorry. I have a talk at the end of the day. I actually got my start onto AST parsing. Sorry. I got my start onto AST parsing when I found out that I actually didn't know how to write UI tests. So I was studying Kotlin metaprogramming at the time, and I thought, I don't know how to do that. What if I use metaprogramming to write UI tests? So that is what I set out to do, which was rather funny because I didn't really know how to do metaprogramming, didn't know how to do UI tests. So a lot of like unqualified things to be started working on this project. It was quite an undertaking. And what I found that was interesting is like the idea was simple. The idea was that I would like to be able to take a Tornado FX, which is, for those of you that might be unfamiliar, it's a Java FX framework written in Kotlin. And actually, this is an example of Tornado FX right there. And so I was using a Tornado FX application, and the idea was you'd be able to upload other Tornado FX projects. It would scan and analyze the code, and from there detect UI node elements and generate tests from them. So sort of a simple idea. The actual implementation part, not so much. I actually had a whole lot of difficulty trying to figure out how I was going to be able to detect those UI nodes. For those of you that might be unfamiliar with Kotlin, there is a thing called PSI, which stands for Program Structure Interface. And that's the most commonly used thing to figure out like certain components of the code for reflection. And then there's also kind of like a little bit of writing back off the Java API as well. But regardless, none of those options actually gave me the ability to be able to detect UI nodes. So after spending like a couple months trying to figure something out, this is kind of how I found AST parsing. AST stands for Abstract Syntax Tree, and the idea is that an abstracted form of trees would be generated to represent the Kotlin code. This is a library that I found, and it's called cast-tree. It's a very simple wrapper around the Kotlin compiler, and because it wasn't very readable, I actually slapped JSON right on top. And this is what I initially found when I started scanning the code, and I'm like, wow, there's definitely patterns here. I have no idea what any of it means. Luckily, I now know what a lot of that means, and it's quite interesting because it's how I got my job at 47 degrees. They were running into some of the same problems I was running into with their project, and I joined the company recently to start working on AeroMeta, which I will definitely talk about more in a little bit. For those of you that might be unfamiliar with 47, we're huge on open source. Actually, the majority of us are Scala folks, and we're very like functional based. The Kotlin team's very, very small. But definitely check out the work that we're doing. Today, we're just going to be talking about AeroMeta. Okay, one of the first things I've learned about this AeroMeta project, the Kotlin compiler, is really scary. I think I only cried twice looking at it in 1 month. I was like, am I dumb? Am I stupid? Am I just not getting this? No, it turns out it's really difficult because we've always had the ability to write compilers for compiler plugins for Kotlin. That ability has always been available thanks to JetBrains and the PSI cookbook, especially if you're looking into IDEA plugins. But the reality is there's not a lot of explanation on how the Kotlin compiler itself works. There's not really like a lot of documentation on that. The architecture within the Kotlin compiler is actually pretty difficult to figure out. It's not intuitive. So I just wanted to say that My background in how I accidentally found AST, and I kind of poked around with it for about 3 or 4 months. I kind of found that we can treat AST kind of as a backdoor to understanding what the Kotlin compiler is. Okay, let's start with the first obvious question. What the hell is an abstract syntax tree? Okay. An abstract syntax tree, as I've mentioned previously, is a form of abstracted representation that's generated and used in several roles actually within the compiler. It's a very, very integral for the several passes that it goes over. And the AST tree is made up of nodes that has a direct mapping to the text ranges in the underlying document. And this is kind of interesting because when the tree is built, it only has like very, very few information at first. And then as we continue to make passes through the Kotlin compiler, there's a lot more information being added over time. And we'll definitely continue to go over that. I kind of feel like the Kotlin compiler is just like trees everywhere. And just to give kind of a preview, we have higher node matches at the top, and then we have bottom nodes that are actually generated from the lexers. So you can consider these to be like really, really tiny components of the code, and then these would be larger components of the code. All right, so that's a lot of information. It's still kind of all abstract. What does AST parsing actually tell us? Well, AST parsing tells us the shape of the code that has been written by the end user, which is us, the developers. And AST parsing actually gives you quite literally everything that you would want in the code except for the punctuation itself. So semicolons and mostly parentheses. Okay, so what do I mean by that? What do I mean by it tells us the shape of the code that the user writes? Well, it's possible for a user to write 2 + 3, and the result is that you would have the larger fragment on top, and then you always end with like these tokens at the bottom. So the reason why I emphasize that is because it's possible to write something that evaluates to the same thing, but the AST tree comes out as a different shape. So for example, you have 2 + 3, it does the same thing, but you have a much more complicated syntax tree. Okay, so quick crash course on the whole AST tree parsing thing. Now we're just gonna go into it with the Kotlin compiler. I think really a lot of like programming is just like anger management and some courage in whatever form you find that. So there's a whole lot of phases within the Kotlin compiler, and I'm hoping to like add some clarification to that before we actually add back in the AST parsing. So we start with the parsing phase. When you have a user writing a Kotlin document and you start feeding it through the compiler, this is the first phase. It's the basis for any compiler optimization. It transforms the input programs in, oh, that's incorrect. I apologize for that. That is, okay. I apologize. I think that's just a slide that didn't, some of that is partially incorrect. So what happens in the first part of the phase is that it generates the AST tree, and what that means is that it starts with like the lexer tokens, and it starts like taking down all the text like bit by bit, and then from there, it actually like composes the tree from that point. The analysis phase is when you have the tree and you start going through you start analyzing it. So like this is kind of the basis for the analysis phase because it's entirely based on the information that you get from the AST parser. And this is kind of interesting because the compiler actually knows nothing about the tree at all. So it starts going through, and then this is the basis for the compiler optimization. And once it starts going through that, it's actually responsible for adding extra information such as like descriptors. It might be performing like some kind of type checking later on, and it starts adding more information from there. And then this is kind of interesting because I want to clarify that AST is not specific to Kotlin compilers. There's actually Lots of different kinds of compilers and lots of different kind of compilers depend on AST trees as part of their process. So I say that because usually when you have your AST, you need some kind of abstracted representation for the code that is specific to your language. So what JetBrains does is they have created PSI, which acts as an overlay for AST trees. Cool. So we've added some information to the Kotlin compiler, and now it brings us to this whole resolution phase. What does that mean? In technicality, it means that we have some extra information from the AST tree, and it goes on to actually generate symbol tables, and on top of that, it can help you generate intermediate representation as well, which is, it's another tree, it's another form. There's just basically a lot of different models that are used within the compiler for different purposes. Very confusing, but we already have the PSI attached to the information that we have. So since we have the PSI, we can actually go through that and do some type checking and enhancements for that. And then at this point, actually you've like kind of reached like almost like the middle end of the compiler, and this is what's responsible for creating optimizations for your IR so that it's able to compile into machine code in a more performant way. Okay, and then finally, you get to code gen. There's not too much about this because this is when we've made our journey all the way from the source code, and we've gone all the way down so that it can be decompiled basically into machine code. And that's like the back end of the compiler. You can kind of think about places where you can make decisions about where you store memory. There's actually like a lot of like concurrent like processing and concurrent like optimizations being done here. So this is like more like CPU architecture and machine level code, and there's a lot with that, but AST parsing has pretty much already has done its job by the time we've reached to code generation. Okay, so we've gone through a crash course of like the AST. We've gone through a crash course of the Kotlin compiler. It was super fast, but we're going to try and smash the two together and see what happens. Okay, so I have taken the liberty of doing a lot of different studies of compilers, and I mentioned previously that the Kotlin compiler itself doesn't really have documentation. So this is one of my first attempts, and any attempt that I know of, to try and kind of debunk what the hell the Kotlin compiler is. So there's several stages. We kind of like went through some of them, but this kind of goes more into what these specific jobs are. So we start with the lexer, and the lexer is responsible for lexical analysis. It breaks the code into a sequence of tokens, and then this is basically creating the nodes that would be responsible for creating the tree. And now that we've generated these tokens, we go to the syntax analyzer, which builds the AST tree. Once that AST tree is built, it has several jobs later on in the compiler. So after this particular phase, we're going to have to analyze it. We're going to have to augment it with additional information. And then we'll be looking to like transform some of that in the resolution phase. Great, so we have our AST tree, and this goes into semantic analyzing. This is largely responsible for type checking and other forms of semantic analysis, likely to verify not only that the language bits that you wrote is correct, that the types you wrote is correct, but that it's also going to compile correctly. And also at this stage, what comes out of this is that since we already have our AST tree, and we have like some overlay on that, we have the ability to generate symbol tables and intermediate representation for lower level mechanical jobs, I guess. Okay, so we've come out with basically our symbol tables, our AST tree. This is great. We have multiple trees, and we have some tables, and we have a symbol table and probably also a table for the associating IR tree. what do we do with that information? From there, we go into the intermediate code generator. Since we have all this information, we output some of this intermediate representation. So, like I said, it's not quite the same as AST because AST is actually more friendly, more relevant for us, the viewers, the visual part of the code. The intermediate representation is meant to be more agnostic to basically any language, and the intermediate representation allows us to do additional analysis that would be more CPU related for the architecture. So this is basically what's responsible for creating things like call stacks and control flows, and there are other forms of analysis as well, I suppose, like data flow and whatnot. Okay, so we output some unoptimized intermediate representation trees, and we did some work to optimize some of that. So here's the back end, the final part, the code generation that comes out of this. So kind of a I hope that this kind of like shed some light. I know we did like basically 3 different passovers of what the Kotlin compiler is, and then we took the same thing and then fed the AST through that process, and I hope that shed some light on some of this. I think a lot of this was really illuminating for me, and it's particularly relevant because it is really important to the work that we do for Aerometa. I think a really great question to ask at this point is like, how exactly does AST relate to PSI? Because IntelliJ benefits from the PSI, but I don't, like, why would it matter to us? I think it's an important question to ask ourselves, because when I was originally looking in my own project and other people have like thought about writing compiler plugins, the only thing that we actually had available to us was PSI or bytecode, and there was like no in between at all, which was kind of a little bit rough, to be honest. So I just wanted to bring this guy back. Here's an AST tree, and we have the top of the node is like usually your element, actually file. You have your binary expression, and this is kind of fun because basically there's different kinds of binary expressions. You could have, sure, you could have 2 plus 3, but you could also have things like something equals something else. It could be lots of different things. So there's lots of different forms of binary expressions. There's lots of forms of expressions. It's actually really interesting to kind of see like what you'd kind of come up with. But PSI tree actually reduces some of that information, and on top of that, there's actually a lot more things in this. Like there's a lot more underlying things within this. These are some of like the PSI elements that exist in the Kotlin compiler itself. This is like the structure that they've created. But within that, usually they'll have some information about the tokens. They'll have some information about descriptors, synthetic descriptors. It's all arbitrary names, but they have a lot of information, just not necessarily covering everything that I absolutely need. Okay. Some of you might be wondering, like, how did I do all that? You know, like just put together some of these structures, because they're actually, a lot of it was poking and prodding at first, but then if you use IntelliJ, this is a really, really great plugin that I really enjoy. It's called PSI Viewer, and basically if you're looking at any, if your cursor's on any bit, it'll basically highlight like where you're at. I really like this because I think it's a great way to kind of explore like what does PSI look like. I like to say that like AST and PSI are actually like very, very closely related. Like mostly for the sake of discussion, they're like more or less the same thing, as long as you understand that PSI is missing some things that AST would give you. But this is still a really nice tool to kind of understand where things are coming from. And on top of that, this is actually a great starting point to start digging into the Kotlin compiler, because their file structure is, like I said, is not very intuitive. It doesn't make any sense. And I think this was a great starting point for me to start understanding like where to start looking and how do things fit with each other. All right, so that is all the information that I can give you on PSI parsing and the Kotlin compiler and kind of like my journey with it and what I know about it now. And I thought that this would kind of be a great opportunity to share a sneak preview for what we're probably going to be sharing at Kotlin Conf this year. Has anyone used Arrow, or at least heard about Arrow, at least? Okay, cool, cool, cool. So Arrow is a project, an open source project maintained by 47 Degrees, and the idea was that there were some functional programming folks that really like Kotlin but would like to see it be more functional. So Arrow was created so that we would have the ability to write things in Kotlin like higher-kinded types. And I think we have like a lens plugin. We have a couple different plugins. We have the ability to do type checking. So it's quite cool, actually. The only problem was that we needed like a special runtime to be able to run some of these things. And we have this thing in the Kotlin community called Keeps. It's sort of a GitHub thing. It's like an issue tracker where people put in ideas about their language. So a while ago, we put in a keep, I think it was like keep 87 to add the ability for type checking. And I think we got a little impatient and decided to figure something out for ourselves. And that's how Arrow Meta was born. All right, so Arrow Meta, at its core, intercepts the AST and its resulting models. And by doing that, it's great because AST actually allows us to alter the level of surface language without changing the rest of the compiler, although in most cases we can and usually do. This is extremely important and significant, not only for Arrow Meta, but really for the community, because the work that we've done and the code that we've written has basically created like a window to the Kotlin compiler so that other people that might be interested in writing Kotlin compilers can do it with extreme ease. Okay, so this whole compiler phases is coming back to haunt us, just in a different form. And with Arrow Meta, we actually have several different phases. So we have our code, we have our interception at AST, and then for the analysis phase, we actually take advantage of the PSI that's generated to lay on top of the AST so that we're basically able to expose the elements that we need that we wouldn't have been able to get before. The synth resolution is actually kind of more of an Arrow-specific thing because synthetic descriptors in Kotlin are not the same thing as like synthetic descriptors in Arrow. And at the end, we have code generation with the ability to enable and generate IR if we wish. And then there are actually other forms of like models that we can take on as well. Also, within Arrow Meta, if you want to write like a compiler plugin or an idea plugin, we have the ability for you to create, to easily like add configurations to your Kotlin compiler. There's that enable IR that I was talking about. You actually didn't have the ability to do that before. It's quite funny. I was trying to figure out how to create IR trees early on in the job, and it was really frustrating because it was not easily accessible. And I think I was like looking around, and some guy from JetBrains was like, "Can you just look at the bytecode?" And I'm like, "No, I need the intermediate representation." So we have the ability to give you that. Okay, we also have other low-level DSLs, which is great because we have like things like IR class, IR function. We have the ability to suppress diagnostics. This is actually super helpful for us, especially when we want to override certain types, like take different sources of packages, and it might freak out in the IDE, but it allows you to build and run otherwise. Okay, great. Now, this is what Arrow Meta basically looks like if you're someone trying to use Arrow Meta and you want to write a compiler plugin. We have a DSL system where we start with like our meta, and then we always like write some kind of extension function as a plugin. And it's rather nice because once we have our meta initialization in here, this is actually where the AST bit starts coming into play. I'm currently in the process of building out the entirety of the quote system. Today I took a break, I guess, for this trip and this talk. But I'm really excited because myself and another person have been working to expose every possible KT element, and we haven't found them all quite yet, but I think we're making a major dent. So I think that's kind of exciting because we'll have, okay, so we have the quote system here, and what this actually does is that it starts with a predicate. So you'd have some kind of predicate where it says, okay, kt.qualified expression. If we're analyzing the code and we find some kind of element that matches this type and it contains an fx block, then we're going to do something to it. Very simple idea. So, oh, out of order. And once we do that, like once we have located the particular kind of code that we're looking for, it could be anything. I think for our lens plugin, we check, is this particular type a product type? So kind of fun, kind of cool. Once you find the result, you can actually transform the code. Actually, you can do it at a couple different levels. Transforming the code actually does it at a surface level because you're replacing the PSI itself. So that's like the visual component, the front end component. So you replace the original code with some kind of flat map version of it. We also have the ability, because we have the ability to expose IR, we also have the ability to transform the code at bytecode level if we wish. All right, so we also have templating that goes with our element scopes. I think we saw a little while back, we wrote a predicate. We're like, wait. Oh, so we have the ability to add templating so that this is kind of like how we're able to change the code fundamentally. So here is the result. We take the expression. This is actually part of the quote system as well. We wrap everything in an object called scope, and it not only allows us to give exposure to the PSI elements that we have, but it also allows us to safely change those elements. Oh, very cool. I don't know. There we go. All right, so the end result is that you as a user have the ability, like when you write a plugin that allows you to change the behavior of the Kotlin compiler, what that really means is that the behavior changes for you as like as the experience of you for the coder, but it also changes the fundamental functionality of the code as well. Apparently clickers don't allow you to press play. So if you're, this is a sneak preview. I think it was kind of fun to talk about one particular aspect of Arrow Meta. There's definitely a lot more to that. But if you're interested in hearing more about what Arrow can do, because really I only talked about one thing, which is just the ability to transform your code and transform the behavior of your code. But I mean, the possibilities are kind of endless. I'm sure some people would come up with more imaginative things than I would. But if you're interested in hearing more, definitely keep an eye out for myself and 47 Degrees at KotlinConf this year, because we'll be revealing a little bit more. We won't be talking about AST parsing as much. But I hope that you guys are really excited about the possibility of writing compiler plugins. Even if you're not a Kotlin user or anything like that, I think this discussion is extremely important and really revealing, especially when we're talking about how compilers work for languages, but also more or less, like, I think we as developers should have the ability to have total control over how our languages and the CPU architecture works as well, especially if it fits for us. So it might be a little bit chaotic, but I'm here for it, and I hope you guys are really excited about it too. Thank you so much.